In this video, we are going to look into production potential of annual and perennial species. We take an example in Ghana, where we grow an agroforestry system with grevillea, banana, pineapple in layer 6, 4, and 2 respectively, and yam. Also, we add compost to add nutrients to the soil. The first thing we check is the plot cover by species, and we see to what extent our plot is covered by the 4 species that we plant. Now, it's very important to realize that before you go to biomass, yield, carbon, we first check the limiting factors. Is everything going all right? Do my species actually grow? So this graph shows the integrated production potential per species limited by all growth factors. And all growth factors are water, NPK, management, acidity, salinity, pests and diseases, temperature. These factors all determine the final integrated production potential. And here we see it differs for the 4 species. Now let's go over them one by one. We start with water. This graph shows to what extent water is limiting production. And for all the species separately, we can see the production potential for every year based on water. And this graph, it's a result from hydrology, water per species, and then the grevillea requirement. So this is how much the plant requires. And this is how much is actually taken up. And the difference between requirement and uptake then determines the production potential for water. Let's continue with NPK. Very often, nutrients are one of the most limiting factors for potential yield. If we look at grevillea in this case, we see that the production potential is quite high. This graph is again a result from soil, NPK potential, actual uptake. And here we see a similar graph as we saw with water. If we look at potential uptake versus the actual uptake, we can see the difference in the NPK that is taken up and the NPK that was actually needed for full potential growth. So the difference in actual and potential uptake defines the production potential for NPK. One of the reasons that it's quite high here is because we added compost. If we would remove the compost, this will yield fewer nutrients in the soil and the production potential is likely to go down. And indeed, we see that the production potential is going down quite a lot. Let's add it again. And then continue with management. All annual and perennial species are defined with a certain sensitivity to poor management. And in this case, you can see that especially yam is sensitive to poor management. Now this has to do with the farm management. And if we would change the technical capacity, for example, to 90%, the production potential is likely to go up. And we see indeed that it's going up. But for the different species, it has a different effect. Now let's go to acidity. In this case, you can see that all species have 100% production potential based on the acidity. All annual and perennial species are assigned with a certain optimal soil pH value. Now it's important to be aware that by selecting a polygon or a GPS location in this map will generate a location-specific soil pH value. This one you can also define manually, and let's say we change it to 5. And in the graph you can see that banana doesn't perform so well anymore because of the changing soil pH. Now let's change it back to how it was. And then we continue to temperature. And for temperature there are 4 graphs. Survival temperatures. For some species it might be too cold or too warm to survive. If we look at banana, the minimum temperature to survive is 0 degrees Celsius. And then if we look at the actual daily minimum temperature, we see that temperatures are high enough for banana to survive. Then growth temperatures. Here it's defined when species start growing and when species start growing optimally. So for banana, the minimum temperature for growth in general is 14 degrees. The minimum temperature for optimal growth is 22 degrees, and then the actual daily maximum temperature is far above these requirements, meaning banana will perform optimally. Then if we do show months, we can see even over the season it reaches above 22 degrees. Now this is especially relevant for temperate climate systems. So if we would try this agroforestry system meant for tropical climates in a temperate climate, let's say somewhere in Wageningen, so we generate a climate from the Netherlands. We see that temperatures are actually dropping below the minimum temperature for growth. And if we do show months, you can see that temperatures are just too low for banana to grow optimally. Also, we see a lot of messages where it's been communicated that our plants are dying. And if we look at survival temperatures, you can see that banana is dying in month 13, 14 because temperatures are too low. Then if we look at all season temperature, we can see the production potential over the whole year. And we see that the growing season is likely to take place at these points. Here, temperature is simply too low. The temperature graph, it shows the production potential only during the growing season. And this is important because if you do show years, these two graphs are different in the way that this is the production potential during the growing season. This is the production potential over the whole year. Now let's go back to our original climate in Ghana instead of in the Netherlands. Here you can see temperature is doing fine, and then the overall production potential is defined based on all these separate limiting factors. And if you do show graph info, it is described into more detail how exactly this is calculated.